In this second part of the recording with the chemistry of the environment introduction, I'm going to talk a little bit through the four Earth spheres that I mentioned at the end of the previous part: Geosphere, Atmosphere, Hydrosphere, and Biosphere, with a brief overview of some of the key information for each of them. Starting with geosphere, also called lithosphere, the solid Earth, 90% of the geosphere is composed of oxygen and silicon, combined making the compound silicon oxide, SiO2. There are also small amounts of iron, aluminium, magnesium, and other metals. On the next slide, I have a list of some of the key components of the Earth's geosphere. It's a layered environment, both chemically, the different chemistry, the different layers have slightly different composition, and also mechanically, they have different physical properties. Oxygen is the most abundant component of the geosphere, a bit over 62%, and well behind other elements like silicon, aluminium, iron, etc. Oxygen is very reactive and is not found on its own as the oxygen atom or even the compound diatomic oxygen O2 in the geosphere. Is bounded mostly to silicon in forming silicon oxide, SiO2 units. There are different interactions between the geosphere and the other Earth spheres. For example, there are interactions between geosphere and atmosphere, and you can think of, for example, the eruption of a volcano, which is going to release a large amount of water, dust particles, ash, and also sulfur dioxide into the atmosphere, changing the composition of the atmosphere. With the hydrosphere, water speeds up chemical reactions that make and break minerals and aids in the erosion process. Many elements, both metal and non-metal ions, are soluble in water. Many salts are soluble in waters. Others, on the other hand, are non-soluble in water. Sometimes whether they are soluble or not will depend on the pH of that water. Think of a water body, think of a lake or an ocean or a river, but also think of rain. The pH of the rain, the composition of the rain will also affect how it interacts with the minerals, with the chemicals, with the salts found in the geosphere, and may or may not solubilize particular elements, and they might be in a different chemical form. Many elements can exist in more than one state. For example, if you think of the element chromium, the metal chromium normally exists in ionic state, forming part of mineral or dissolving in water, and it can exist as chromium 6 plus or chromium 3 plus. The different oxidation states, the different chemical state of the elements will affect their reactivity and also their toxicity, and we will be looking at those interactions throughout this module. There's also interactions between the geosphere and the biosphere. The nutrients released from rocks during breakdown, erosion processes can be dissolved in water and then can be used, uptaken by plants or in a water body by aquatic plants. The Earth atmosphere, that thin shell of gases and some suspended particles that surround the Earth and separates the Earth's surface from space, from the vacuum. Very unique chemistry, contains oxygen and carbon dioxide, carbon dioxide is in very, very small quantities, but as we will see, you probably already know this, but we will definitely see throughout the module, a very, very important gas, and it supports the atmosphere, supports life on Earth. You have there a list with some of the major components of the atmosphere in the near the surface of the Earth. We will see later on that the composition changes as we move away from the surface towards the space, the different layers of the atmosphere. Mostly nitrogen, 78%, with around 20-21% of oxygen and small quantities of other gases. And you can see that some of them, for example, look at carbon dioxide and methane, a very, very small percentage of the atmosphere. However, we will see that they are fundamental in some of the chemical, biological, physical processes in the Earth. Chemistry in Earth life, since they are involved in global warming, when they are when their quantities are increased by human action. And we will be looking at global warming in one of the sessions of this module, in one of the weeks in the module. We will look more at this slide when we study atmospheric chemistry. So this is just an advance of what the type of chemistry we are going to be looking at. And if you see, there's quite a lot of information in this slide, and this will be common to one of the other sessions of this module. The idea that when you look at the graph, you see all the information that you can extract from the graph. So interpreting graphs, interpreting information presented in a graph form is one of the key aims in general for all level 5 modules, but specifically for this one, this sort of developing your discursive and interpretative skills. Different layers of the atmosphere, troposphere, stratosphere, mesosphere, and thermosphere. You have information about how big those layers are. You have the name, the poses, tropopause, stratopause, and mesopause, the places where one of the layers changes into the next one. You will see on the right the degree of penetration of incoming solar radiation. Different wavelengths of the sun will reach different layers of the atmosphere, and that will determine the chemistry of those layers. And if you look at what it says, principal chemical species, this section here, you will see that the elements themselves do not change that much. Nitrogen and oxygen are present throughout the whole atmosphere. In the bottom layer, in the troposphere, you have some argon, some CO2. When you go up, you find mostly nitrogen and oxygenated species, but the species themselves are not the same. Look at, for example, if you compare the troposphere and the stratosphere, the nitrogen is in the form of N2, diatomic nitrogen, or molecular nitrogen. The oxygen is in the form of O2, molecular oxygen, also called dioxygen. But look at the species O3, introduced because there is sufficient energy in that layer of the atmosphere, sufficient energy and the right wavelength to promote the formation of the species ozone, which is highly reactive and gives rise to a huge, very, very interesting chemistry, the chemistry of stratospheric ozone, that we'll be talking about in one of the sessions of this module. We move a little bit up the mesosphere. We start getting protonated species, for example, N2O plus or O2 plus or NO plus. So ions, positive ions, cations. Those are rare species and you will see that they are not found in the troposphere or even the stratosphere. What I mean is rare is that it's unusual for N2 and O2 to become protonated. The structure is stable enough that in normal circumstances, the compound two nitrogen atoms join, two oxygen atoms join, are perfectly stable. One atom of nitrogen and one of oxygen for making nitrogen monoxide, NO, are stable. However, the radiation, the solar radiation in that layer of the atmosphere, in the mesosphere, the wavelength that penetrates that layer of the atmosphere allows that much more rich chemistry of covalent compounds that typically would not stabilize well a positive charge that do in those conditions. And it's a very fast chemistry. Those compounds are very complicated, many different species that normally you would not find, that because of the energy and the wavelength of that solar radiation in that part of the atmosphere, those species are stabilized. And if you go a bit further up to the thermosphere, you start finding really, really very rare species like this O2, O plus species, that protonated atom of oxygen, which is extremely reactive. You would not normally find in ground in a normal chemistry experiment, but because of the energy and the wavelength radiation that penetrates in that part of the atmosphere, in the thermosphere, that species is stabilized. And you also find interesting species like this oxygen atom or the nitrogen atom. So atomic nitrogen, atomic oxygen, which again you would not find normally. Both nitrogen and oxygen appear in a compound. The compound might be N2 or the compound might be O2, but they are bonded. Those both nitrogen and oxygen are too reactive and do not normally appear on their own as one atom, one single atom. But again, the radiation, the wavelength of solar radiation that penetrates the thermosphere is sufficiently to allow for those species to form, which are very unstable and they react very quickly to produce all the other species that appear in that section. So we will spend a few sessions looking at this sort of very rich chemistry of the atmosphere and the different processes that happen in different layers. We will be concentrating specifically in the troposphere and stratosphere, which is where some of the key environmental processing atmospheric chemistry and some of the key pollution problems in atmospheric chemistry, in air pollution, happen. Interactions of the atmosphere with the other spheres of Earth, with the hydrosphere. There is an interesting exchange of gases in the atmosphere that dissolving water bodies, and we will be looking at the dissolution of CO2, how other elements like, for example, nitrogen, oxides, etc., including CO2, dissolve in water bodies. With the biosphere, key fundamental processes, change of oxygen and carbon dioxide, which are essential for life, the process of photosynthesis and the process of respiration. And with the geosphere, again, the gases in the atmosphere that react with water to produce weak acids, or sometimes when there is and we will be looking at acid deposition at acid rain, not so weak acids that change the pH of the soil, that aid in the erosion process, that changes the chemistry of the geosphere of the soil. We will be looking at the hydrosphere, and we'll spend several sessions looking at the chemistry in water and the chemistry of the bodies, and how to keep track of the different species depending on the characteristics of that water body. You have the hydrosphere, can be liquid, oceans, as well as lakes, river, etc. Also groundwater. You've got solid water, the polar ice caps, permafrost, snow covering in the high mountainous regions in which there is always permanent. And there is also the gas form of water, which exists in the atmosphere. There is a small amount of water vapor in the atmosphere. And how we will be looking to the way water moves throughout the Earth, through the different spheres of Earth, because of evaporation, precipitation, etc. Processes, which changes where the water is in the cycle on Earth. We will be looking at the chemistry of atmospheric water and processes, for example, of acid rain, which can be called more properly acid deposition, since it can be liquid or solid deposition. We will be looking at some of the physical and chemical properties of water bodies, salinity, a bit of information about tides, the forces that change the composition of the gases and the solids dissolving in those water bodies, depending on the depth of the water body. There is a lot of water in the Earth. Very little of it is fresh water. This is a lovely graph from a United Nations Environment Programme a report called Vital Water Graphics Report. It was published in 2002. And it kind of shows that although, yes, there is a lot of water, around 73% of Earth's surface is covered by water, a very, very small proportion of that water is fresh water. Most of it, of that 73% of water available on Earth, 97 and 98% is salt water. So around 2.53% is fresh water. And of that fresh water, only a very small amount, around 0.3% is kind of readily available as lakes and rivers, and around 30% of that 2.5 in groundwater, soil moisture, swamp, and permafrost, of which some of it is available, groundwater, but others like swamp water or permafrost or even soil moisture is not that readily available. And most of that fresh water is actually in glaciers and permanent ice and snow cover. We will be looking in several sessions about on the interactions between the hydrosphere and the other spheres of Earth, how water is transferred between the hydrosphere and the biosphere and the atmosphere, and how not only water is exchanged, not only the water molecules move across the different spheres, there's also energy exchange in the process. And not necessarily a lot in this module, but also we will be touching briefly in the aspect of water and in the interactions of water and the geosphere, and the sort of weathering aspect of that interaction, the breaking down of rock to form loose rock and eventually soils, and how that changes the landscape, the surface of Earth. Finally, we'll be touching throughout the whole module in the on biosphere, living organisms. As far as we know, we haven't. The sphere that distinguishes our planet from all the others, at least in the solar system. The chemical reactions and the chemical composition of atmosphere, and how that changes in the interaction between the atmosphere and the biosphere. and the fact that, something like the fact that we do have 22% of our atmosphere is composed of oxygen, which is why we have life, and that is largely a product of the photosynthesis process. So with this, I conclude this part of the session. And in the final part, we will be looking at how chemistry links all these different environments. And I will be showing you a few diagrams that we will then go on to explore more in depth in future sessions. So thank you very much for listening, and I hope this recording was useful. As usual, if you have any questions or comments, either post on the chat for this week or just drop me an email. And please feel free to organize a tutorial if you need further clarification of any specific part of what I've covered.